So good morning. I am Krishna Kumar. Welcome to Krishna's class. We continue with the discussions on linear transformations on R. In fact, what we would like to do is to go for very concrete representations of linear transformations. So let us see how we do this. Now I take more general scenario like talking about linear transformation from Rn to Rn. So before we go to the matrix representations, we'll start with the general notations and so on. So we take x to be equal to Rn, y to be equal to now let t from x to both x and y are linear spaces, initial addition and scalar. Now we consider all the linear transformations from x to y. That means you have x here, y here. Now E is a linear transformation. Now you see you have the entire class of linear transformations. And this collection, see you have got say another so this is of x, this is dx, this is s, x and so on. So you have got now various linear transformations in fact, we consider the entire class of linear transformations from x to give a name to it. So we define it as L. So this is the class to be set of for T. T is a linear transformation. Exclude. That will be our standard notation. And when x equal to y, that means we are talking about linear transformation from a linear space into itself, then we use the notation Lx. So we shall use that we have. Now we can introduce, see, this class of objects, what are called the linear transformations from x to y, also acquire the linear space structure. Because here the basic sets that you have are, that is x and y, are both linear spaces over the same field. I think I have to mention that over the same field and then we have all the linear transformations from x to y. This is denoted by Lxy, and this collection also acquires a linear space structure. because the spaces x and y are both linear spaces, and the transformation that we are considering is not any transformation but a linear transformation, which means it has a property that gels with the basic structure of both x and y. Therefore, we can expect some nice structure for Lxy to inherit, and that, in fact, as expected, is a linear space structure. So let us define this. So how is this? Now we prove that Lxy is a also linear space. How does that come? Now, to say that with addition defined by p plus s x now this is well defined. So this is a new addition that we are defining on Lxy, and that is defined in this way. So also you need scalar multiplication. Scalar multiplication is Ct of x is defined by C of now T S belong to Lxy and C belongs to, that's the definition. So we have defined addition and scalar multiplication on the space of linear transformations. Now we claim that this is a linear space. Okay, first of all we have to make sure that T plus S belongs to Lxy. So claim Lxy so what do we have to show? We have to show that T plus S is also a linear transformation from x to y. How do you do that? It's very simple. So you have to verify this. I will do it at one stroke, or I will do it this way. So you have to do this T plus S y let me use x1 plus x2 equal to for x1 x2 are equal. That is one thing that is to be verified. The other one is C of This is what you have to prove. Now I will just show you how you possibly do this, because you have to start from here and reach out here. Okay. So t plus s of x1 plus x2 equal to t of by the definition of addition. So what we have to use this result. And then of course we use the linearity of t. So this is equal to tx1 plus tx2 plus sx1 plus sx2. Now that's equal to t plus s x1 plus t plus s. So that, and similarly t plus s so it's straightforward. This I leave the proof to you. Okay. Right. Therefore t plus s is linear. That is so for t belonging to t belonging to Lxy, s belonging to Lxy, t plus s belongs to L of x plus y. Similarly, verify that for C belonging to R, X, T belonging to Lxy, Ct belongs to, this is quite straightforward. Okay. Therefore, you see that the addition of two linear transformations give you a linear transformation. The scalar multiplication of linear transformation, is also a linear transformation. So addition and multiplication, scalar multiplication that we have defined, does not take you outside the space Lx1. Okay. Now all that you need to verify is the other properties. Like with respect to addition, it's an abelian group. So you have to know, you have to identify what is your zero element. So the zero element is the zero operator. Okay. So we set the identity element addition is the zero operator. Say 0 such that 0 of equal to 0 this 0 belongs to the 0 of y. This 0 belongs to okay. So the inverse element for t minus t is now you can verify all the properties of a linear space. Now verify. Now, of course, there is a question of coming if X is an n-dimensional vector space and Y is an m-dimensional vector space. What is the dimension of Lxy? So that we will answer in the context of what we do. Okay, so I am not going to give a separate group of that, but you can elaborate on that and ask for what is a possible basis for the space incidence. Okay. So we now look at the possibility of getting a what you call a representation, more concrete representation for the vector space. Now we have seen that the choice of the basis is not unique. Okay. Therefore, we start with working with by fixing a basis for x and fixing a basis for y. Now you know that you are working in Rn and Rm, x is equal to Rn, therefore x is n-dimensional and y is m-dimensional. Since I am working on Rn, I'm just deliberately keeping x as Rn and y as Rn. It is something that we can easily drop in this assumption. X is an n-dimensional vector space over R and y is an n-dimensional vector space over R. And even more generally, you can talk about x is an n-dimensional vector space over F. F is an associated field and y is an m-dimensional vector space over C. For instance, Cn is an n-dimensional vector space over C. I mean, these are all, very straightforward generalizations that you do, but all the essential features of all the computations involved is reflected here. Okay. So, what does this mean? So, let Vx an ordered basis and Vy Now we fix these two things for the rest of the operations. Okay. your bx and by, which are ordered bases for x and y respectively, then you have unique representations for vectors in x and y with respect to the ordered basis. So this is something readily available. So let x belong to x. Let x be given by alpha 1 x1 plus where alpha 1, alpha n are individual. Now what one does is this. So we write alpha, the column vector, this is a matrix, this is an n row, this is an n by, or what you call it, it's a column vector. Denote this by alpha. Okay. Now one observes that Px equal to, okay, so if P is given, then P is completely determined by its action on x1 on dx. That is true. So any linear transformation is completely determined on what it does on a basis, because for any arbitrary element, once you know what are the images of x1, x2, etc., xn under t, then you can manufacture the image of an arbitrary x. Okay, so that is very clear. Therefore, let us define. So let the x1 be given by, it's a linear combination of, so tx1 is in y and therefore it's a linear combination of vectors in by. Therefore, let me write that, and I write it as the following: tx1 I write as summation over I running from 1 to m a I1 y. Okay, and more generally, okay, Pxj equal to sigma I equal to 1 to m a ij so also Txn, you will get sigma I equal to 1 to m a I n. Okay, I have written everything, but that is not required. I mean, so I put it in the following way. You know that these are the coefficients. Aij's belong to R. They are uniquely determined. Therefore, what you have, I will write the general expression. The general expression is that T one to m So this is the general expression where Aij's belong to. Okay. Now let us look at the picture. What is emerged? I think that's so. You have x. You have P is a new expression from here. Now what do I have? I have here. So this is x going to P x, right? Then you have, you see, you have a ordered basis that you have chosen, which I write as x1, xn. This is the set x. So I can write here yx, which will give an isomorphism to R. What is the element? The element is alpha. Okay, and alpha is given by the entity alpha 1, alpha 2. This is the point. Now what do you get on this side? On this side, you see that y, so this is Rn. Now you see, you have a certain image of this under with respect to dy. Say Tx has an image given by beta z, which is equal to some beta m. Okay. Therefore, what do you have? Given x, there is a t. T carries x to Tx. Tx is mapped from here by the isomorphism phi y to the element beta. And in short, corresponding to x, you have an isomorphic image alpha. Therefore, corresponding to alpha here, there is the corresponding x here, there is the corresponding Tx here, there is the corresponding beta here. Therefore, each each alpha there is a unique beta, that is beta beta. Okay. So let me designate the corresponding map connecting alpha to beta by bracket B. Let us see what this looks like. Okay. So this is essentially a map from Rn to Rn. There are a few things to be done which I leave it you to work out. Now you see, you have now the first thing that you have to verify is this. What is it? This bracket T map is a linear map from Rn to Rn. How do you infer that? I mean, it's quite easy to infer, because you take x1 and x2 here, and then you have the corresponding or x and z here, then there is a corresponding images here. So x and z will go to dx and dz, and then you have the corresponding images here. Say this is, if I call this alpha and gamma, then I have beta and say some lambda or something like that, the images of that, and then I can consider this. Otherwise it is quite easy to see. See, this phi x is an isomorphism between x and Rn. Therefore, it's a one-to-one onto linear map. Okay, so its inverse is also a one-to-one onto linear map. Okay, so alpha to beta is written like this. Okay, so you have T of alpha equal to beta. But what is T of alpha? See that T of alpha equal to, what is beta? Beta is you start from alpha. So you start from alpha. First apply phi x inverse. You are here, and then apply T. Then apply both phi x and phi y are isomorphisms. Therefore, they are linear maps. They are one-to-one onto between the respective spaces. T is linear. Therefore, you see that this is true for every alpha belonging to R. Okay. Now you see that this is linear, this is linear, this is linear, and you can show that the composition of linear maps is again. Okay. Therefore, what you have is this. Therefore, T is identified with phi y T. Okay, and phi x, phi y are isomorphisms. T is linear, and I can write here linear isomorphisms to be and T is linear, hence in fact you can do an elaborate working on this. Quite easy to see that. In fact, the ingredients are, if you have two spaces, say x and y, you have two spaces x, y, z. Suppose you have a map from here to here T. You have a map from here to here S. Both are linear. Then it defines a map from here to here, which is actually S T. Prove that S T is linear. T is linear, S is linear, implies S T is linear. So once you do that, then this is obvious. So T from T belongs to S belongs to L, Y, Z, then S T belongs to L, so once you prove that as an application, this becomes, so I don't have to work on it. I'm not going to do it. Oh. Okay, right. Now, so that is done. Okay, it's a linear transformation from Rn to R. Therefore, now let us work out the structure of this more clearly. So for that, we have this information. Now alpha x is equal to, so x is equal to alpha 1 x1 plus alpha n. Therefore, what is Tx? Equal to alpha 1 Tx1 alpha n Tx1. Now you know that Txj is given by that. Therefore, this is equal to, I can write this as sigma. You can write here from j equal to 1 to n alpha j Exj, which is equal to sigma j equal to 1 to n alpha j sigma Aij I running from 1 to this is it. Okay. Now let us rewrite the whole thing. So I just take out this part and then write because I want that. I don't need this. So I just write this. So what I have is this. So this is to indicate that this is a continuation is here. So this is equal to, what do we have? See, these are all finite sums. Therefore, interchange of summation is possible. Therefore, what I do is bring out this alpha j can go inside and so on. So what I have is that this is equal to sigma. Therefore, Vx equal to sigma I equal to 1 to Aij alpha j this I write now let beta I is equal to beta I will be equal to sigma j equal to 1 to n Aij alpha j. Now this is what I define. Then you have Tx equal to sigma beta I so what does this mean? Therefore you take beta column vector okay, therefore this is what it is. Okay, so what I have is that the operator T maps alpha to okay, so let me write here a bit more elaborate. So let me write here. So what do I have? Tx I get as this. So x I get as x is identified with y tx is identified with okay. Therefore I have now beta equal to now you write this in terms of this one, so that we have computed dx we have computed somewhere, dx is computed here, so we get actually sigma I equal to 1 to m sigma Aij alpha j running from 1 to n, this is equal to sigma so what is one obtained? So we obtain each beta I equal to, so beta I this is the conclusion of the. Now we immediately observe that the matrix multiplication can be used to represent this. So what does this mean? This can be written as beta equal to the vector beta equal to the Aij alpha, where Aij is matrix with real entries Aij. I remember from 1 to okay. So that's what you get. Okay. Therefore, this I can denote by, so let yes, this is an m by n matrix. Now I am assuming that you know the basics of matrix theory, addition of matrices, multiplication of matrices, etc. etc. So that is assumed. We assume it. Okay. So this is the expression that you have done. So we have now obtained a matrix representation for this. So if you are, keeping the bx and by fixed, then you can drop this and simply write square root of b is equal to this. So once bx and by are fixed, then we shall write just I want a bit of caution at this stage. We wrote txt equal to sigma aij yi, fine, but the summation was on I, okay, not on j. Our instinctive our instinct is to write txi equal to aij yj, okay, but we have done it deliberately the other way around. That is something to be noted. It's only because of that you get here aij, where you know that aij is the ith row, jth column element. So what one does is this aij comes here. So you have got the matrix here. There are, so this is the ith row, and jth column, this is the jth column. Okay. So you have got the ith row, jth column. There are I runs from say 1 to you have n rows and n columns. 1 less than or equal to 8. That's the structure. Okay. To get this in this form, in our usual standard notation, you have to be careful here. This is what I said. Look at the way in which you don't take it casually, but if you don't do it, I mean everything will go through, but then you will be getting a different representation. Doesn't matter at all. But then one would have to be careful when it comes to matrices. Your usual, what you registered in your brain cannot concur with what you obtain. So it is immaterial, but that is true. So what you have is this. So I will write it this way. Essentially, this is what you get. Beta 1. See that it checks. So this is what is called an m by 1 matrix. Now this is an m rows and n columns, and this is n by 1. And you know that an m by n multiplying an n by 1 matrix will give you an m by 1 matrix. So that is something to be observed. Okay, so this is called the matrix representation. This representative depends on so you know that there are infinitely many choices of the ordered basis that you can choose. So depending on what ordered basis you choose is going to determine this Aij. In other words, what you are saying is that the same T has several possible representations, and they can be obtained by changing Vx and Vy, because you know that you have plenty of choice of Vx and Vy, and that essentially determines your infinitely many choices. Okay? Therefore, this gets, in general, T has infinitely many possible matrix representations which can be determined by the choice of dx and dy. So once you fix dx and dy, then the representative of t also becomes fixed. So this is what you get. Okay. So this is not the representation P by the matrix is not depends on choice of dx so that is the first observation that we make. So we got a matrix representation. Okay. Now we shall also work on the following. Now let us see what happens when you take the composition of operators. Okay. So let us now consider the composition. Okay. So let linear spaces over R of dimension N, M and P. That is dimension of x equal to n, dimension of y equal to m, dimension of z is equal to p. Therefore, we have, so let be a basis for y and let so we take T to be S belonging to L Y Z. Then ST is belongs to L Now this is something I leave it you to do. So the picture is this. You have x, you have y, you have z. So this is n dimensional, this is n dimensional, this is p dimensional, this is p, this is so you start with an x, you get px here, you map here, so you get apply s here, so you get s of p. Okay, so this is the image. So this is essentially you have the map SP. Okay. So this is S of Px. So ST is defined from X to Z. But remember, TS is not necessarily defined. In general, TS is not. Yes, it's not. So one has to be careful about the order in which you choose. Okay. Now let us write down the following. Let Pyi sigma B K I K running from 1 to I equal to 1. Okay. Now what do you have then? So let ST Xj defined as sigma Kj So we go by our earlier definition of S and T. Okay, therefore let us start working with this. Now you see that T so S of P, this is equal to S of sigma I equal to 1 to M A Yj Yi this is equal to sigma I equal to 1 to M A Ij S. Okay. Now this is equal to sigma I equal to 1 to Aij sigma SYI we already have here. What is that? SYI. I think we have to find here. SYI. I'm sorry, I think I should write here. SYI, I can write this way. So I write, I will simplify AIJ, SYI. So please note the error that I have made earlier. So this is equal to summation over K BKI BKI okay, and that I write as summation over AI summation over, I interchange the summation. I can do that because it's a finite sum that we are talking about. So the interchange of the summation is permitted, and what do I get? I get here summation over I E K I into A I J I coming from 1 to N. Okay, right. Now I have defined here. So I have Zk equal to Ckj equal to Ckj equal to. So comparing this one. So from I have Ckj equal to sigma Bki Aij because these are two representations, they represent the same thing, therefore this is there. Okay. Now this is for 1 less than or equal to k, less than or equal to p, 1 less than or equal to j, less than or equal to therefore, what do I get? So I have now a matrix. So the matrix for S is given by Ckj, which is given by summation over 1 to m B Ai Aij. Okay. Therefore, what do I get? I get here. Therefore, this is equal to. You see that this is the kjth element of the product of the two matrices. What you call the product of the two matrices. Matrix S. Okay. So this matrix is, what kind of matrix is that you have here? P is the matrix M by N, and this matrix is P by M. Okay. This is a P by M matrix, therefore the product is going to be, so this is a P by M matrix. Okay, so it's a P by N matrix. Right? So you get the matrix of S, which is P by M matrix, the matrix of N is M by N matrix, and then you take the product is going to be a P by N matrix. So you have the picture here, X, Y, Z, you have P, you have S, you have X, Dx, Sx. So this is the picture that we have. So correspondingly, what you get in terms of matrices? In terms of matrices, I draw it. So the picture that you get is the following. You have X, Y, you have corresponding here R, N, its image R, M, its image when you have an X here, goes to Dx, goes to now what do you have? You have to, this is corresponding to Dx, there is an image, and there is the image of this corresponding to dy, and here you have the image corresponding to d, all the three bases of that. Now what you have then is this. This is your alpha, this is your beta, this is your alpha. Okay, so this corresponds to the matrix T, this corresponds to the operation through the matrix S, and you see that you have corresponding to this matrix, this is ST, you have the corresponding map here. So ST is identified with ST, and that ST is, so you have S, So this is the initial value. Right? This is the general scenario. So you have now an M by M matrix. You have now a P by M matrix, and that will give you a P by N matrix. Okay? So this is given by what you call. So ST maps alpha to gamma. Okay? ST maps alpha to gamma. That's the picture that you get. Okay, so you see that your matrix multiplication is essentially an offshoot from the possibility of representing linear transformations in terms of matrices. Exactly. Okay. So it is a mathematical meaning for a matrix can be obtained in terms of linear transformations between respective spaces. Okay. Once again, you see that all this representation depends on the basis that you choose. But however, this formula, whatever be the basis that you choose, once you fix the basis, the matrix of ST is the same as matrix of S into matrix of T, and that's an invariant. This product rule is an invariant. Now this is a beautiful outcome of this. Okay. So now let me just go to the scenario where x equal to y equal to z. That's the one that we often use. So we take x equal to y equal to z. Then it is immediately seen that you are talking about T belongs to x. Now given T and x, T comma S belonging to Lx, both Ts and St are okay. So what you get? So let x1 be an ordered basis. You choose then say let it be designated by dx. Now let me write dx. Now you have the corresponding expression Sx also, so also S that's a condition. So then what you have, when you are talking about, you can completely look at these two figures. From there you get the idea. So you see that both ST and TS are defined because your domain and range are the same space. Okay? So now we make some inferences. Suppose T is inverse. Let I denote the identity. Namely, I of then you see that in any basis, the matrix representation for is given by which is equal to both the 1 less than or equal to I, comma A is equal to A. This is the identity matrix. So irrespective of what ordered basis you choose, as long as you choose the same ordered, once you fix the ordered basis, then you see the identity map is represented by the identity matrix. Identity matrix is along the diagonal you get 1 and otherwise it is 0. Okay? So one observes that suppose T is 1 to 1 and on, then T inverse exists and is linear. So you have both T, matrix of T into matrix of T inverse equal to matrix of T inverse, which is equal to matrix of I, and that's equal to okay. So this is a matrix, this is another matrix, and so also T inverse T inverse E which is again equal to theta. So you have the matrix of T into the matrix of T inverse. So you have the I, and that implies the following. That implies the following, that equal to the inverse of the matrix T is equal to the matrix of T inverse. So inverse of matrix of. That's an inference that we do. Okay. So you have now the following picture. So you see you have X. So this is an n by n. An n by n. So you have got T here. Then you have Rn, copy of Rn. You have the same copy of Rn because we are keeping yn by equal to bx for convenience. And then you have the map from here corresponding to bx that we call it phi. And then you have got alpha. This goes to beta, and this is px. Px is mapped to phi is again corresponding to the same bx. Okay. This is the picture that you end up with. Or in other words, you have the matrix T is equal to inverse phi to make some observations. If T is invertible, then maps a basis bx onto a basis, that is x1 xn is a basis for x implies T x1 and this is true. So T is a one-to-one onto map, that is T is an isomorphism of X. So we have T is an isomorphism of X if and only if the matrix of T is invertible. Conversely, if T is a matrix is invertible, then the operator determined by that invertible matrix is X. Okay. So given a matrix, an invertible matrix, it determines a linear transformation. How is it? So the matrix is given which maps alpha to beta, then T is determined as follows. Okay. So once alpha is given, X is fixed through the basis. Then once beta is given, the corresponding element is fixed by this basis. So how is the linear transformation defined? T is defined as phi bx. So you see that T is defined by as follows: bx equal to phi bx acting over x, then okay. So this is true for any t. This is in fact true for any t. Okay, not necessarily this is true for any t. For n cross n. So you see that you have now a connection between the two, namely that Lx is identified with certain kind of width and equivalence relation. This is the following. So the equivalence relation is this. So we define as follows. A comma B belonging to we say A is related to B, B comma B, there exists an invertible C such that I think I'll stop here today and then continue from there. Okay? So thank you very much. Now we will explore this and then look at the possible connection. Okay?